So it's 6 now. I guess we should start so that our speaker can also go back to his other commitments. Well, hello everyone, and welcome to our seminar series on models, learning, and sensing in hydrology. Before I introduce today's speaker, I would like to invite Dr. Abubakar to formally start the seminar series.
Thank you, Javeria, and it's really an honor and a pleasure to welcome Dr. Intikhabi as the inaugural speaker for this seminar series. This is a new series that we are starting here at LUMS, and the roots of this idea actually goes back to some conversations that we were having among colleagues. A couple of them who are present here. So Javeria is here, and of course, Dr. Zara Lakawara has just joined us, and Talha is also out there. And we were sort of thinking about these new intersections that we are seeing now in the field of hydrology, especially disciplines like machine learning, remote sensing, robotics, mobile sensing, citizen science. And I think in recent years, we are viewing new intersections, new applications, and some very deep science as well. So what we thought was that perhaps we should set up this series basically as a way to educate ourselves, to connect with the area experts, and to learn from them what is really going on in the field there. Also, we are lucky that within our ranks, we have started to receive new faculty, fresh faces. So Javeria is one example of that, and there are other fellows and faculty members who are coming in, who are bringing in new ideas and fresh ideas. And lastly, there is a lot of interest in the industry as well as the government sectors to deploy some of these new ideas into the field, especially regarding the grand challenges that we are facing in water, in agriculture, in environment, and so on and so forth. So I think the timing for this is very pertinent. We also received funding from the German Academic Exchange last year for a project on which myself and Dr. Zara, they are co-PIs, and we are actually investigating some of these ideas into that project. And also within our NCRA Agricultural Robotics Lab, there is a lot of activity which is going on, which overlaps with these ideas. So it was within this broader framework where we wanted to learn from the experts, we wanted to explore new ideas, and this is how the series was conceived. So I'm really looking forward to this, again, learning from others, and also making hopefully some contributions down the road. I'll hand over to Javeria, and good luck with the series.
Thank you, Dr. Bakr. It is a great honor for me to introduce today's speaker, Dr. Dara Intikhabi. Dr. Intikhabi is a professor at MIT. His research interests are in land-atmosphere interactions, surface water and groundwater coupling, and Earth remote sensing. He is the science team leader of the NASA Soil Moisture Active Passive, also known as SMAP mission, which was launched in 2015. His research has significantly advanced our understanding of the Earth's hydrologic cycle. Today, Dr. Intikhabi will discuss the detection and mapping of shifts in dominant hydrologic processes using satellite data. At the end of the presentation, there will be a question and answer session. I advise the audience members to please type your questions in the chat box, and the presenter will then address them at the end. With that, I will hand over the virtual mic to Dr. Intikhabi, please.
Thank you so much for the invitation to speak to the group today, especially in the area of modeling, learning, and sensing in hydrology, which is a shared interest with the group. It was always great to visit LUMS during Januaries in the last few years, and the highlight was always visiting the Water Center to discuss with colleagues interests and activities. So it's been remote for a couple of years, and the seminar is remote as well. So rather than sort of diving deep into one technical topic, I think the purpose of a seminar is a sort of discussion, taking a step back and looking at what we're doing rather than just describing one technical study. So with this, I want to take a oops. Okay. let me just clear my screen. Okay. So in the hydrologic sciences, as in other disciplines, sort of quantum jumps or shifts usually follow when a new type of measurement becomes available. Not more measurements, but a new type of measurements. And the reason for that is that, let me also get a laser pointer. Okay, here we are. Is because new types of measurements allow us to look at processes that were not observable with prior measurement systems. And it not only affects how we understand processes, but it affects also how we model things. And in our area, one of the new measurements that have become available recently is the state variable of the landscape. And that is soil moisture. So the state variables of the land surface being soil moisture and soil temperature, and the fluxes are go on the sort of the right-hand side of the equation of the change in state variables. So the state variables, temperature and moisture, link the fluxes such as runoff, drainage, and evaporation, and control them. But we really have never had mapping measurements of soil moisture. So this is something that for us is a new data type. And the question is, now what with this new type of measurements? And recognizing that measuring the state variable and tracking the state variable is a new type of measurement, a proposal was put together for spaceborne remote sensing of this variable. And the justifications are fivefold. These are the high-level requirements for a mission that were defined, and they still hold today. Three of them are sort of basic Earth system understanding, and a couple of them are in the applications area. And this is not the only or exclusive uses of the data, but sort of the very obvious ones. And in the science area, again, because soil moisture is a state variable of the terrestrial water cycle, it also serves to link the water, energy, and carbon cycles. And the key word there is link, as we'll see in a second. The three main metabolic cycles of the climate system, of regional climate and global climate, are the water, energy, and carbon cycles. And remarkably, over land, this is the process that soil moisture is a variable that links them. And so one main objective to understand how they are linked, both in the water and energy cycles and the carbon cycles. And if this link is not properly accounted for the three main cycles, it leads to a divergence of model projections of how regional climate will evolve, and things like water availability, temperature, stress, and so forth. In the area of applications, soil moisture has long been recognized as a key in the operational domain as well. For instance, just droughts, agricultural drought by definition is a persistent deficit in soil moisture. But in operations, like an example here, over counties in the US, the anomalies in soil moisture are based upon, or drought severity are based upon model soil moisture. So soil moisture accounting, not observations. Similarly, flash flood guidance or main stem flood guidance is based on modeled soil moisture in the operational. Here, example is the National Weather Service, because the runoff ratio, how much of the precipitation is partitioned into runoff and infiltration, is very much dependent on the antecedent soil moisture. So how moist or saturated the landscapes as a sponge is will determine how much of the rainfall will translate to a flood, or will it be all absorbed. So this being the guidance, the technological approach to do it is to sense the surface. So you want to go into very low frequency microwave. Reason being that you want to see right through the atmosphere and through clouds and even precipitation, and even be able to see below the vegetation canopy as much as possible. So when you go to a low frequency as low as 21 centimeter wavelength, very close to what cellular phone networks are operating under or thereabouts. So obviously we can use cellular telephone communication even in all weather. So this is the frequency of choice. And in order to be able to make these measurements, to have a antenna that can focus on the surface, you have to have a very large aperture antenna. So what you see here, the concept was a 6-meter antenna, and it's a lightweight mesh. So it folds like an umbrella and unfurls like an umbrella. And then this thing has to be scanned by rotating around itself in order to have a mapping of the surface and not just a pencil beam measurement. So the soil moisture active passive or SMAP mission was born out of this. It's got, this is the radiometer, and it had a radar which failed after 3 months. I'm going to come back to this. The radiometer has very high sensitivity to surface soil moisture, but at very coarse resolution, around 40 kilometers. But the radar has less sensitivity, but much higher resolution. And the idea was the combination of these two gives you an intermediate resolution, intermediate accuracy measurement. So this mission was finally launched in 2015. So now we have 6+ years of data that much of my talk is going to be based on. And here's an example of the data on this scale. On the right, you see soil moisture in volumetric water content. So it goes from 0 to porosity around 0.6 on this scale, but it varies obviously around the globe. And that's what you see over land. But over oceans, we also can detect the salinity of the surface water. So this is in practical salinity units. And you see where there's lots of evaporation, you have high salinity, where you have rivers flowing, you see the plumes coming out of the Amazon. And these two, and salinity is a state variable of the ocean, as well as its height and temperature. And these two are very much linked, because over land, soil moisture is the difference between precipitation and evaporation. And over oceans, salinity is evaporation minus precipitation, the inverse or the reverse. So these two are state variables of the water cycle across the globe, not just over land. So in water resource management and hydrology have a shared history, and not only shared, but they feed one another. So the need of water management decisions drive the development of hydrologic models, and hydrologic models support water resource decisions. For example, in water resource management, the persistent question has been how much water is available for withdrawal or use. So the focus of hydrologic modeling has been very much on stream flow. And since the runoff volume is bounded by precipitation, in order to predict stream flow, we have focused a lot on observing precipitation and using models to partition that precipitation into stream flow and landscape storage. And stream flow is, again, bounded by precipitation, but it's a delayed and dampened version of precipitation. So the structure of the hydrologic models so far have been a series of reservoirs that serve to dampen and delay the output. And an example of it, a classical approach to hydrologic modeling is so-called the conceptual hydrologic model, where the input is rainfall and snowmelt, precipitation, and the ultimate output, where all the arrows end, is stream flow. And everything in between are a series of storages that again serve to delay and dampen the input signal. So this is input, output, and this is the sort of the system that delays and dampens things. So the main requirements so far have been to characterize the input precipitation, measure the outflow, and then calibrate maybe a dozen or so parameters inside the system that translates the input to the output. Again, the output being bounded by the input, but delayed and dampened. And this is true of not only this sort of operational hydrologic models that are used in water resource management, but also in land surface models. They're very similar philosophy. You have a system that is composed of a bunch of reservoirs. The only input, as the arrow suggests, is precipitation. And then you have outflows like evaporation, runoff, and a change in storage. So very much similar philosophy, different application. It's an input-output system with a number of parameters to calibrate. Again, the focus is on the input and the output of the system. And traditionally, regardless of whether it's operational model or land surface model, we have deployed around the globe many such rain gauges and many such stream gauges. This is a stage measurement that gets translated into outflow. And these are the available observations when the discipline was defined and how we approach modeling to this date. In order for these two to be adequate measurements to account for all the water in the system, we have to define the fundamental unit of analysis as a watershed, where there's a watershed boundary, which is the ridge, topographic ridge, across which there's no flow because it's a ridge. So this is a capture basin or a catchment, and the only input into it is precipitation from the surface, and the only output is the stream flow at the outlet. So this being a no-flux boundary, the input and the output are related. In fact, the output is bounded by the input. But over the last few decades, the questions in water resource management have changed. The driving questions have changed, and so has the capability to monitor the landscape. So before, where I had posed as the main driving question, or the main sort of conversation between water resource management and hydrology, is how much water is available. The questions that are being asked now in water resource management are more subtle and more diverse. So we're talking about equity and rights in water resource management. We're talking about ecological fragmentation, integration with urban landscapes, water cooperation, climate change impacts. And these are questions that were not being asked when the handshake between water resource management and hydrology led to the development of the kind of models I've been talking about. So what these new questions require is maybe revisiting the basic unit of analysis. Ecological fragmentation, equity, and rights are not necessarily following the watershed boundaries. And in fact, just looking at, again, basic state variable of the surface temperature, if you look at satellite images of infrared temperature, and we look at some political boundaries, not watersheds. Here's the boundary between Sinai and the desert and the Negev. And here's a boundary in the US-Mexico border. The land use is resulting in a change in the system, change in the landscape that does not follow necessarily any watershed boundary, but it follows political boundaries. And these questions apply to that kind of situation. So topographic boundaries are maybe not the basic unit of analysis that we need. What we need is to map the real conditions on the surface and generally map them, as in spatial mapping. And also we need to look at ecological variables at the same time. Urban systems within the domain of analysis are no longer exceptions, but the rule. And we need, for climate change impacts, look at the energy and carbon balance as well. So mapping necessarily leads us to remote sensing as a efficient way of having a spatial coverage that is not possible by just having in situ measurements and networks. And in remote sensing, there's always a trade-off, and it's in this, to simplify it, is a three-way trade-off. One is spatial coverage, so that allows mapping and monitoring. So in remote sensing, that is well covered. But there is a spatial resolution and a temporal refresh rate that are depending on what technology you use for remote sensing. There's always a trade-off between these two, and sometimes spatial coverage as well. So we'll come to this trade-off in a second. So back to our traditional measurements, the input-output systems. These are available from heritage measurements. But now we have satellite systems that in various ways can map the surface and yield different information about the surface. And these are transformative technologies to go from this to this. And the question is, does it require a rethinking of our conceptual models to interpret and use the data in hydrology and water resource management? And much in the history of hydrology, a lot of models have been developed, and just like in natural selection, only a few of those models survive. And the fitness criteria for hydrologic models has been to extract as much information from the available observations, which is traditionally has been precipitation and stream flow, and to do it with fewest of parameters, hence the conceptual models, and fit the performance metrics defined for the problem. So models have survived, or the models that we see today are the result of this natural selection, which is very much dependent on the observations that we make. But precipitation as input, stream flow as output have been, with a few number of parameters, has led to the conceptual hydrologic models or land surface models that we see today. But when we get a new type of data, besides precipitation and runoff, this disrupts the natural selection process. And is similar to in nature, the evolution drivers change the structure of the system. So for instance, one of the observations of Darwin when he was in the South Pacific was to look at the finches in different islands, and he noticed that their shape of their beaks, which is an evolutionary trait, is dependent on the food available to them. What sort of types of seeds or other flora and fauna is available to for them to evolve. So here we see the environment driving the natural selection. Same thing in hydrologic models. So let's go back to this hydrologic model. Again, applies to LSM as well. We got rainfall or snowmelt precipitation as input, stream as output. But if we have soil moisture observations, we're observing the state of the system rather than the input and the output. We're observing what's inside here, which we've never really looked at because that was not the point. The point was to get the best output out of the input. So one chance that we have with remote sensing of surface soil moisture is to turn the problem inside out, to look at the dynamics of the inner workings of the system rather than just the input and the output. And ask the question, what are the hydrologic processes going on that we need to capture? So let's look at a typical time series of remote sensing soil moisture. So this is again soil moisture measured in volumetric water content units. And this is date. This happens to be a location, I believe, in Oklahoma or something, doesn't matter. It's just showing the dynamics of soil moisture over this particular location. And we have basically soil moisture, for instance, going down over a period of no rainfall, interstorm period. There's a storm, soil moisture jumps up, and then it decays again, jumps up, decays again, and so forth. If we take the time derivative of this, it looks something like this, the change in soil moisture. This coincident the vertical line, so during this dry down period, soil moisture increments are negative, it's going down, and the rate that it's going down is decreasing. And then there's a precipitation event, so there's a positive increment in red, and then there's a negative increment, positive increment, negative increment, and so forth. This is a stationary process statistically, so it's not indefinitely going up or down. So the average of the blue and average of the red must balance in the long term. And in fact, they do. Here's the probability density function of the positive increments and the negative increments. And the average, the mean of those is the red line and the dashed red line, and they're coincident in the long term. But the distribution around the positive and negative increments are very different. The distribution of the red is very different than the distribution of the blue, the negative increments. What's the signature of hydrologic processes encoded in this difference in distributions? So let's look at one of these dry downs and look at what's going on. Just look at one dry down. So there's a pulse of precipitation. This is soil moisture versus time. Pulse of precipitation, so soil is wetted. It very rapidly drops to a volumetric water content that in hydrology and agronomy we've known as the field capacity. That's when gravity drainage is stops, and it takes more force than gravity to remove water from that soil matrix. This is a well-known threshold. And then there's a period of dry down, which is no longer gravity drainage, but dominated by evaporation. And then there's a period in that evaporation process where the rate of falling of soil moisture gets less and less and less. So if I look at the rate at which this is changing versus soil moisture content itself, it looks something like this. So you have soil moisture on the x-axis, and this is the loss processes that lead to this negative increments. So at the beginning of the storm, the soil is very wet. You have very high gravity drainage rates, so basically free drainage, until you hit this field capacity. Now drainage process stops and evaporation begins. But the soil is quite moist. at this stage. So evaporation is limited by available energy. So it doesn't matter what the soil moisture is, how much you can evaporate depends on how much evaporation demand there is in the atmosphere. So the rate of loss is constant. It's determined by radiation and not soil moisture. So it's invariant with soil moisture, as the flat line suggests. But then you hit a threshold where the available energy is plentiful, but the soil matrix is holding back the water. So we enter the so-called stage 2 or water limited evaporation. And as the soil dries, the rate of loss becomes more limited because the soil matrix, the capillary forces are holding back water. So the increment, the delta theta, is dependent on soil moisture thresholds and different processes in each of these zones. So basically what we have is the rate of loss, the change in soil moisture, negative increments per unit time, conditioned on soil moisture. So conditioned on this axis must be this loss function. And here's an example of this time series plotted in this way. So we see evidence of a stage 2 water limited evaporation and the beginnings of a energy limited evaporation rate. And it never really gets moist enough to have a drainage in this particular unit. So we can use the time series to identify these thresholds based upon just this simple conditional expectation. When we map them over the US, we get a picture that is expected, but never really shown with data. The water limited regime, this is the percentage of time in water limited regime, is dominated in the semi-arid West. The energy limited is dominated in the upper Midwest and sort of more eastern US. And gravity drainage, remarkably, is dominated in this area in the upper Midwest. A good fraction of the time is gravity drainage. And we're going to do stuff with this, but just as a aside, this area of gravity drainage coincides remarkably with where we have installed tile drainage for agriculture. So tile drainage is when you the landscape is so moist that crops cannot grow. So horizontal canals and submerged pipes and tiles are a network of them called tiles are installed in the subsurface in order to drain the landscape. And this is percentage at county level. This is obviously land surveys that tile drainage is dominant. So in a sense, that's evident in soil moisture dynamics from space. Now, as I mentioned, these are patterns that we expect, that the water limited would be more in the West, energy limited more in the East, but it's more than just an obvious pattern. These boundaries shift year to year. So, for example, this is 2015, and this is 2016 and 2017, with 2015 as the dark lines, just to see how much they move. So in 2017, there was a flash drought in Montana and South Dakota. So we see that what used to be green is now red in this particular situation. So, and that has consequences, as we'll see, for energy and carbon balance. Now, going back to this time series, we estimated the loss, and that is fine. But really what we're interested in is partitioning this loss into drainage and evapotranspiration. We haven't done that. We just had this total loss. What can we do is, without assuming a model, but just representing the processes that we were just discussing in the most simple functional form. So evaporation, for instance, loss has a stage 1, what energy limited, and a stage 2. So if that is all we want to capture, doesn't matter, define a function that has this behavior, that it goes up monotonically and then it plateaus. So this is a function, doesn't matter what it is, it's a parsimonious function, it has a B parameter, which is critical, which makes it shift left and right, and the A parameter obviously shifts it up and down. The drainage is just a power law, which is gravity drainage. This is from soil physics. This is just unsaturated hydraulic conductivity under unit gravity. So we basically fit the observations, what the satellite sees, to what we believe it should be seeing, based upon a water balance model that is adjoined using a Lagrange multiplier over the period of observation. So this is a variational approach to estimating those parameters. There were 4 parameters, 2 for evaporation and 2 for, this is evaporation, for drainage. So we get from variational simulation parameters A, B, C, and D. But that's not the point. The point is to estimate the fluxes. So from these parameters and these functional forms, we can estimate the evaporation and the drainage. These are the climatologies of them, but we obviously estimate them for every day in units of millimeters per day. So this is a mapping from space using the simplest of functional forms for the processes that we know to exist. How do they compare with flux towers or USGS stream gauges, geological survey? About 70% of the variance is explained for these point measurements where there are coincident. But these are not necessarily apples and apples. These are point measurements in towers. These are area average. These are over basins that are aggregated. And also there's hydraulic structures going on. So over these units, we get the total precipitation partitioned into drainage and evaporation. So these are the major basins in the US. The blue line is the precipitation. Now we get the partitioning. So the way conceptually we're thinking of this is that soil moisture time series has a marginal probability distribution function. So this would be a marginal distribution function turned to it on its side here. These are the loss functions, evaporation in green, drainage in blue, the total in black here. So this is a derived distribution problem. This is the PDF. This is how the functions depend on it. So we can do a derived distribution. Now, we can probe the processes. What if we increase precipitation by 25%? What if we decrease it by 25%? The partitioning under normal conditions is 76-26 in this particular location. So 3/4 evaporation, 1/4 drainage. When we increase precipitation by 25%, the partitioning changes to 65-35. When we decrease it, it goes to 90-13. So if the system was linear, these partitionings would not change. So obviously the system is quite nonlinear, and the way it exercises that nonlinearity, so this is the nonlinearity, the way it exercises is by the marginal distribution and how it shifts from year to year. So we can look at the few years of satellite data, estimate the nonlinearity, and then run historical precipitation going back to 1948 and look at how year to year the partitioning is changing. So here's the PDF of all those years, the nonlinearity, and this is the cumulative density function of evaporation and drainage. Now, we can look at some basins. I give you the worst example and the best example. This is the worst example. This is the time series of USGS streamflow measurements. This is what we estimate as drainage from the satellite data trained nonlinear model. And here's this traditional cumulative density function of the streamflow predicted and observed. Not very good. And another case which works quite well, this is the year-to-year variability, and this is the cumulative density function, this is the CDF of streamflow. It does quite well, and the partitioning changes from year to year. So one contributing factor here is that this is a snow-dominated basin. This is a non-snow-dominated basin. So obviously we didn't capture snow processes at all. And then we can ask questions like, how important is the nonlinearity? So this is an example, again, USGS observed streamflow cumulative density function. Here's the prediction. If there was no nonlinearity, that means the partitioning was a constant. And here's the partitioning with a variable nonlinearity that is in the system. So it obviously tilts the CDF towards the observed. So the nonlinearity matters. One last thing I want to get into is, with water resource management questions shifting more towards landscape, water stress, and climate change, what do the measurements tell us about these three main metabolic systems in the climate: water, energy, and carbon cycles? They're very much linked together, and the linkage is through a few processes that I'll try to very quickly explain here. Let's take a Earth system model and reduce it to three equations, just for conceptual reasons. There's the water balance, change in soil moisture over some hydrologic active depth, precipitation input, evaporation output. The change in temperature is incoming radiation, outgoing radiation minus the sensible and latent heat fluxes. And the carbon budget is the evaporation times how much exchange of carbon is associated with that, minus some senescence. The variable that links all of them in this case is evaporative fraction. How much of the available energy is actually going into evaporation? Evaporation is water loss, it's energy loss, and it's carbon gain, photosynthesis. So evaporation efficiency is a non-dimensional function of the state, soil moisture, and water use efficiency similarly. So to see why do regional climate projections are so far from each other, here's 6 Earth system models. Doesn't matter what they just represent 6 different models, some domain. Here's evaporative fraction versus soil moisture in the model, and carbon flux versus soil moisture in the model. And there's wide range of behavior, and each of these will link the water, energy, and carbon cycles differently. So hence the divergence in the predictions. Now, in order to have a benchmark data set, we have to observe each of these independently without the use of models. So for the x-axis, we have SMAP, soil moisture. For evaporation, we have weather stations. And for carbon, we have a measure of photosynthesis, which is the amount of fluorescence that is going on. It's a measurement directly proportional to photosynthesis. And here are the purely observed evaporative fraction, purely independently observed soil moisture, and photosynthesis. over some regions in the US, and we see the stage 1, stage 2 evaporation clearly with some landscape dependence. Again, purely based upon observations. And the same behavior is in the carbon flux, but the plateau is different because there are different vegetation types in each of these, but the same sort of threshold behavior that's controlled by soil moisture. And here's the water use efficiency versus soil moisture. Is very hyperbolic as over these locations. And this hyperbolic relationship has been observed in laboratories where they put plants in a chamber, torture it in various ways, and see how its water use efficiency changes. So they see in a chamber a water use efficiency which is hyperbolic, and this is looking at it from space and mapping it. And kind of questions that in water resource management we asked today is the land surface response to change, is it necessarily coincident where you have the largest climate forcing? So conceptually, we ask if this is the climate forcing, regional climate forcing, like precipitation change, is the land surface response just directly proportional to that? So this is all we need to know. So again, we try to map the land surface response by looking at the temperature, diurnal temperature amplitude. It's a measure of how much energy flux there's going on. This is from satellite data. And this is the PDF of soil moisture. We have a response function, and we can then sort of go back to that conceptual figure. What is the land surface response with respect to climate variability? And we see that that threshold, that time spent in water limited versus energy limited regime, determines the sensitivity, the slope of these curves. And if we define a measure of tipping points for land surfaces, if you're 50% water limited, 50% energy limited, you're right at the tipping point. If you're always in the water limited, the probability is higher, and if you're always in energy limited, lower. But the sort of crossing the threshold is maximum, where your probability of water limited is at 50%. So now that we know those thresholds, we can look at the tipping point and the severity of the tipping point across the globe, which regions are most vulnerable. I want to conclude with going back to one of the things I mentioned, that the resolution of the measurement I quoted as 40 kilometers. That's just sort of based upon the antenna pattern. And you can see that by just looking at a region like, someplace in Georgia. This is May 5th over Georgia. These are the measurements with the radiometer only. The cities are masked out because over urban regions, you can't, it's too much non-natural soil or no soil. So these are the main cities in Georgia, and the distances are several hundred kilometers. So it's a pretty coarse-grained view of things. And we lost the radar, so we can't get the resolution. But there are other radars operating out there, like the European Sentinel radar, which is not on the same platform. It's an independent satellite. So whenever they're coincident, we can use the radar measurements to get high resolution versions of the sensitive radiometer measurements. So this is what you see at 3 and 1 kilometer, for instance. It looks broadly the same as it should. They should be consistent, but it's got a higher dynamic range because it's not smearing what it measures, but actually looking at local variations. So the resolution is much higher but the revisit, the refresh rate, that's the trade-off I was talking about, is 10 days rather than about 10 days rather than 3 days. So it's lower revisit, but much higher resolution. And sort of closer to home, I just want to show what one can do with higher resolution. Here's a familiar map with the river and regions of high amount of irrigation. This is FAO percentage of land under irrigation. And when you look at the radiometer measurements, you see these regions of high irrigation being higher, but it's kind of pixelated when you look up close. So let me go back. This is the percentage land irrigated, large region here, large region here. And broadly speaking, you see these appear as more moist, but very coarse resolution. So let's go back to this same figure again. We notice there's this canal with that goes north-south, and there's irrigation around it. And when you look at the same picture in high resolution, you sort of see the remnants of a high soil moisture irrigated landscape over there. So in summary, very broadly speaking, the concerns of water and environmental management today have changed, and they require revolutionary shifts in what we consider a unit of analysis. It's no longer an aggregated watershed, but the real landscape with all its complications due to political boundaries and cross-basin transfer and land use and others. And we need to characterize all of those in real mapping, not just aggregation for the convenience of water balance and the watershed. And as new types of data become available, we need to really rethink, but more importantly, retool how we use that data and model them for short-term predictions. So thank you for your attention. I'll stop there.
Thank you very much. This was an illuminating talk. I'll first open the floor for the audience members. I have received some questions, and if there are any more questions, please feel free to type it in the chat box. So I'll begin with some questions that I had and then also that I received, starting with the concept of drainage versus evaporation. So when you choose the term drainage, does it mean just the subsurface flow or the surface flow as well?
Drainage in this case refers to loss of moisture from the top few centimeters of the soil. So it's mostly gravity drainage. It may go into the subsurface and into the groundwater system and eventually come out as a stream flow, or just get added to the, so it's not a storm runoff, but it's what goes into the soil and drains to the groundwater. Eventually, it may become stream flow or base flow, or it may become sort of in the riparian zones evaporation. But it's a loss from the sensing depth or sensing equivalent sensing depth of the soil. When you look at 40 kilometers, those kind of lateral exchanges, for instance, storm runoff likely will be re-infiltrate. So it's from a broad scale, it's what's not lost as immediately is very rapid drainage.
Right. We have another question. We have a question from an audience member. So Dr. Mohammad Ali is asking, what is the effect of vegetation greening over water resources of a region. So the coupling between vegetation greening and then water resources within a region.
Yeah. One thing that I had in the talk, I had to take it out just for the sake of time, was that actually much of the work that I do today is exactly on that problem, because the satellite senses the contrast between soil matrix, the quartz, and water. They have very different electromagnetic properties, and that's the basis of the measurement. So as the signal is emitted from the surface, and it goes through vegetation, it goes through another media, which is the canopy. And based upon the same principles and the contrast between water and carbon in the biomass, it senses how much water there is in the vegetation. So you have two simultaneous measurements, soil moisture and vegetation water content. And you track those day by day. So one thing that a lot of my students have been working on in the last few years is to look at the water exchange in the soil vegetation atmospheric continuum day by day. So how does, when we see the signal in the canopy going down or going up, is that because of rehydration or is that growth? And we can sense that using simultaneous measurements of soil, water, and canopy water. So the question from Dr. Ali is exactly it, is the change in vegetation water content that we see, is that because the plant is growing or is it rehydrating? So those are evolutionary traits developed by plants facing water stress. And that's what sort of the ecology question we're looking at.
So perhaps if you can just comment on it in a general way. The question is that how does runoff influence the underground water storage?
The underground water storage is the recharge that I was also referring to as drainage. Okay, the recharge is how much of the water that's absorbed by the soil during a storm drains actually to the groundwater. And recharge as a flux is a vertical flux from the soil upper parts to the groundwater, and evaporation. So recharge and evaporation are the two most important hydrologic fluxes, because recharge determines the sustainable use of groundwater, and evaporation determines crop production, and it links the water, energy, and carbon cycles. Recharge and groundwater, the two most important fluxes, are the least known fluxes in the hydrologic system, which is remarkable that the two most important fluxes are the least known and least measured. And remote sensing really is a pathway to tackling that problem, because there is no instrument for recharge measurements. There just doesn't exist. We have to do it through residual analysis, which is a dangerous thing to do. And evaporation is fine with flux towers, but how many flux towers do we have around the globe? Nowhere near enough to map anything. And also, I want to mention that these two important fluxes, recharge and evaporation, are the fluxes that have seen the most global change already. Not by 5%, 10%, by factor of 2 or half. Evaporation and drainage, recharge have changed by factors like that. not because of atmospheric composition necessarily, but land use change. We have doubled or halved almost in order of magnitude these two important fluxes, and we can't even track it. So remote sensing is really a pathway to breaking that deadlock.
Thank you for your answer. I see it's 7, so we'll stop the question and answer here. If you have any other questions, please feel free to email us and we'll forward them to the presenter. The recording of this presentation will be uploaded on the WIT official webpage. So if you have any questions, please feel free to email us and check out the recording on the WIT website. So I'll stop the recording here and I'll ask Shabir to end the webinar session. But
Okay.
Dr. Intakhabi, if you could stay just a little bit longer.
Okay, thank you. And thank you for your attention at this late hour. And please do email me if you have any questions.